want to do some computations to help with the homework. So computations. With Smith normal form. Okay, and so this should help us out. So, all right, so let's do a theorem. Well, actually, maybe we should do an example first. Okay, so let's do an example. So Smith normal form is so recall. So given a matrix, over a PID, A, let's say a matrix over a PID. Let's call it. We need to give the PID a name, I guess. R, and let's say A is, an M by N matrix over the ring R. Then by using row and column operations, we can find a Smith normal form. A Smith normal form of A. So that means that A, so like it will have some PAQ is S, and then this thing looks like a bunch of diagonals. Right, and then a zero matrix here. Okay, and it has the condition that A1 divides A2 divides blah, 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 divides AR. Okay, so this is what the Smith normal form looks like. And the idea is that this gives a good presentation. So this gives us nice presentations of modules.
You might be heading in this direction, but that looks different than Dummett and Foote. He's got ones in the diagonal and then the A1 through AM in the bottom right with no zeros. I don't
know. So you can have so yeah, these can be one. So yeah. So what can happen is that these can be ones. So the first couple can be ones. Can be ones. Right, and I guess there's a kind of a difference between the matrix version and the so when you have a 1, it'll just kind of like kill that generator, right? Let me give you an example. Okay, let's do an example. Okay, so let's do an example. All right, and then maybe we can come back to this example in a bit. Okay, so so this is kind of an example problem. So so we will show the free abelian group generated by, let's say, V and W, subject to the relations okay, we'll do V plus 2W is equal to 0, and 3V plus 4W is equal to 0. Okay, so these are the only relations that I'm going to impose. Okay, is isomorphic to Z mod 2Z. Okay, so this is what we're going to do. All right, and so the idea here is that okay, so we kind of have this okay, so what should we call the free abelian group? Maybe V. Or sorry, the okay, so this is V subject to the relation. So it's not just free. This is not a free abelian group, but it's subject to these two relations. Okay. So what we're wanting to compute really is we're wanting to compute. So we want to know the isomorphism type of. So we're going to have Z V direct sum ZW modulo. Then we're going to have V plus 2WZ plus, and then we have the other one, 3V plus 4WZ, like so. Okay, so we're wanting to compute this quotient here. Okay, so all right. Okay, so let me compute what this is. So what we're going to do is we're going to compute the Smith normal form here.
On the bottom, should that be a direct sum or just a regular?
No, I'm just doing a sum. Yeah, that's not a direct sum. I could have written sum on the top too; it'd still be true, right? But yeah, this is not. I mean, in general you don't know that it's a direct sum. So I'm just going to write it this way. Okay, so let's maybe encode this here. So what does this mean? So these are the relations. So these things are the relations. Okay, and so we know our module V here is finitely generated by two elements, right? And so there's a surjective map from Z2. Okay, and then we also know that the kernel of this map. So this is this comes from the generators. Okay, the kernel of this map is the image of this. So 1, 2, 3, 4. Okay, so the kernel of this map. Let's see, Z2. So the kernel of phi is the image of this thing here of 1, 2, 3, 4. Okay, and so what we're going to do is we change basis here and here. So we do a change of basis, and then we're going to get a new presentation here where this thing here is the Smith normal form. That's what we're doing. Okay, so then let's look at what we can do to simplify this. So 1, 2, 3, 4.
Okay, does phi map the image of 1, 2, 3, 4? Because like phi by itself would just be from Z cross Z, right?
So this thing here looks like ZE1, direct sum ZE2.
Yeah.
Okay, and then phi of E1 is V1, and phi of E2 is V2. Or sorry, not V1 and V2, V and W, I think I called them. Okay, and then so let's see what this would be. So like if we did this, so let's look at this matrix. Okay, so let's say that this one has basis E1 prime, E2 prime. Okay, so then this matrix 1, 2, 3, 4, E1 prime. Okay, so this is like the 1, 0 vector. So this is 1, 3. And oh, so maybe I need to take the transpose of this. Sorry, let's see. So this is 1, 3. So I guess I should be taking the transpose of this. Right, because 1, 3, because phi of 1, 3. So this thing here is E1 plus 3E2. And then you have phi of E1 plus 3E2 is V plus 3W. So actually, I want to take the transpose of this. So we need to be actually taking the transpose. So instead of taking the transpose, let's do the following. Let's take the transpose of this. Okay, so I did, so 1, 3.
Wait, you said the transpose of this? What this are you referring to?
This matrix here.
Oh.
Oh, let me actually do it so that it's clear what I'm doing, what I did. So I don't want to mess up. So okay, there we go. Let me go back. Back. Right. Okay. So what I'm going to do is I'm going to take. I'm going to do a different system of relations. I'm going to do V plus 3W, right, is equal to 0. And then I'm going to do, and then I'm going to do 2W, or 2V plus 4W is equal to 0. Okay. Okay, so now this thing is the matrix that I wanted before. 1, 2, 3, 4. Agreed? Okay, so now you see that this thing here is this, which is what we decided was 0 here. Okay, so now I've written it in a way, so, and then now I guess this needs to be fixed. This needs to be fixed as well. So this is ZV direct sum ZW modulo V plus 3W Z plus 2V plus 4W Z. Okay, so this is what we're computing.
Taylor,
Yes.
would this be the same if it was just V plus 2W?
This would not be the same as if it was V plus 2W here.
Okay, thank you.
Yeah. Because we're modding out by the relations given here, right? And so, yeah. All right. Oh, you're talking about this one here.
Yeah.
Yeah, so that would not be the same if you did a constant multiple of it. So you can't factor out by 2 because it has some annihilators. So this is saying that V plus 2W is killed. So V plus 2W isn't necessarily 0, right? But V plus 2W is annihilated by 0.
Thank
Or
you.
annihilated by 2. So this relation, that's a good question. So this relation here, this relation is not equivalent to V plus 2W is equal to 0. So what it's saying, the relation we have is saying V plus 2W is killed after multiplication by 2. All right? Okay. So let's do the Smith normal form. Does that make sense?
Yes.
Okay. So, okay, so let's do the Smith normal form for this one. Okay. And so to compute the Smith normal form, right? Where's my Smith normal form computation? Okay. So what we'll do is you want this top piece here to be to be like 1 or the most the GCD, right? You want this piece to be the GCD of the other pieces. Okay, so 1 is going to be the GCD. Okay, and now I'm going to use a row operation. Okay, and I'm going to kill this piece here. And to kill that piece, I need to subtract 3 times the first row from the second row. Okay, so then I do 2, this stays the same. And then I do 4 minus 3 times 2. Okay, all right. And so what is this thing equal to? So this is equal to, so we did R2 goes to R2 minus 3R1. Okay, this thing is 1, 2, 0, and then we have 4 minus 6, so this is a minus 2. Okay, and all right, so this thing is now I guess I can use the bottom column to kill the top column, right? So this can go down, and so sorry, the bottom row to kill this piece of the top row here. Right, so there's actually 2 ways we can kill it. Generally, what you'll want to do is you can use this, so you can kill using this, or you can kill using this way. It just so happens that the green one works this time, but it won't work in general. Okay, so all right, so now what we have is we go which one? Let's do the green one for fun. Okay, or actually let's do the blue one because we should probably do what works more generally. So now this goes, C2 is going to go to C2 minus 2C1. Okay, and then when we do that, we have 1, 0, this gets to 0, and this is a minus 2. Okay, so now this is in Smith normal form. This is now in Smith normal form. So you were saying that there was no ones in the dominant foot one, or there are ones. I mean, there are ones. So this thing will get. So let's see what happens. Okay. So now we have a new basis here. We have a new set of generators, and we'll take this purple thing, right? And the purple thing goes back into our to this piece here. So this is our S. Oh. This is S. Okay, and so now we know that V, so V is isomorphic to Z2 modulo the image of S. And now this is easier to compute. So the image of S, so S is this thing. Okay, so this looks like, so this is, in the first component, we just have Z, direct sum 2Z. Agreed? So, you know that S of E1, E1 prime, or I guess this is in some new, I don't know, now we need to give this thing a basis here. So let's call this E1 prime prime and E2 prime prime. S of E1 prime prime is, okay, and then this needs a basis too. So, I don't know, maybe we could call this V1 prime, V2 prime. Prime. Well, let's see. Okay, we'll just, yeah, we'll do it like that. Okay, so this thing is V1 prime prime, and SE2 prime prime is 2 V2 prime prime. Okay, so this means that, and then this top one here is the V1 prime prime, V2 prime prime coordinates.
Why isn't it minus 2 V2 prime prime?
Oh, it should be minus 2. Sorry. It is minus 2. But you can scale rows and columns in this procedure here. Okay, and so this gives us, so this allows us to conclude that V is isomorphic to, well, Z mod Z direct sum Z mod 2Z, which is just isomorphic to Z mod 2Z. Okay. All right. Okay, so let me say a little bit about like what the coordinates are. Okay, so let me just make a little remark on some coordinate issues here. Okay, so some linear algebra rules. Okay, so I can never remember how these rules work, but let me kind of tell you let me give you a kind of a spoiler. Okay, so okay, so maybe I should just start with a matrix. So I always forget. So how to remember? This is how to remember. Figure out how change of basis operations change a matrix. Okay. So all right. So let's do this. So I always start with a matrix. So let A. Okay. And we're going to do this A11, A12, A1n, A21, A22, A2n, AMN, AM1, AM2. Okay, so okay, so let this thing correspond to a linear transformation T from V to W, where V has basis V1 through Vn, and W, big W, has basis W1 through Wm. Okay, so what does this mean? So I always look at the first one, so I can never remember how the sum works. I know that like TVI, so okay, I know that TV something is going to be right A something something W something, right? But I never remember what goes with what, right? So what goes with what? So I always just do TV1. Right? And I know that V1 under this correspondence corresponds to the first element here, E1, which is 1, 0, like so. So I know I need to sum over this first column, right? So then this thing goes A11, and then now I need to do it in the W coordinates because we're in the target. W1 plus A1 A21 W2 plus dot 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 plus AM1 W M. Okay, so you can see that here that the first components are the ones that are going to match. Okay, and so TVJ, right, is the sum from I is equal to 1 up to M of AIJ WI. Okay, so yeah, so the i's, although it's the first component, goes with the second vector space when you're summing over the second vector space. All right, so the trick here is, So to remember the rules, just try it out on the first thing. On V1, the first basis vector. Okay? All right. So, okay, so let's look at what happens when we change a basis. All right, so if we do a change of basis, on the domain, what happens on the range? So this will be our new basis vector. So V1 tilde. So I'm just going to try it out. V1 plus CV2. Okay, so I'm making a new basis. So make a new basis. So V1 tilde, V2, all of the other ones are going to be the same, right? Except for this new one is going to be a scaled version of the old one. Okay, and all you do to see how it changes the matrix is you do T V1 tilde, right? That should be, this is the new first column, whatever it is, right? And so you do T of V1 plus CV2, right? And you do the sum from I is equal to 1 up to M of AI1 plus sorry, so we're doing TV1. So AI1, A plus C, AI2, WI, right? So this thing here, this is the new entries of the first column. Right, and so the change of so the matrix changes like this. So so this tells us that the change in the matrix is C1 goes to C1 plus little constant C, C2. So the columns, so the second column gets added to the first. Oh. Okay, so we're going to continue with this. So the thing about the row changes is that they're a little bit more complicated. Okay, so let's do a change of basis on the target now. Okay, so to do a change of basis on the target, let's say W1, so we'll try it out with the first thing. W1 tilde is W1 plus CW2. You can always change something on the target like this. And so now if you do TV1, right, it's going to be weird. So so TV1, right, is equal to, well, you do the sum of AI1 WI, I is equal to 1 up to M. Okay, and so what we need to do is we need to express, so the thing that we need to do is instead of using W1 in this formula, we need to replace with an expression using W1 tilde, the new basis vector. Okay, and to do that, we'll use that W1 is W1 tilde minus CW2. Okay, so this thing looks like AI1W1 plus AI2W2 plus junk, the rest of the stuff. Okay, and now we're going to replace W1. So this is AI1 W1 tilde minus CW2 plus AI2W2. And now this is AI1W1 tilde plus, and now you have so you have a AI2 minus C AI1W2 plus, okay, so now we have to forget the other terms that were not going to be touched. So these are this junk part is the indices higher than 2. So this is, all the stuff that was left over from the sum from 3 onward. Okay, so what does this tell us? So this gives us the rule, right? So the change in matrix here is that R2, the second row, goes to the second row minus a constant times the first row. So when you do a change, when you change the first vector, right, depending on what you change by, you subtract from the thing that you changed by. So it's messed up. The row operations are messed up in terms of change of basis, the change of the basis, right? And this always confuses me. Every time every time I teach this class, or every time I teach a class where I have to do linear algebra, or anytime I do a computation with linear algebra, I always have to remember how this works. If I need if I need to know how my row operations are working with an explicit basis, right? So, all right. So the general rules are as follows. Okay. So, here's what we have. So the change in basis. Okay. So if I replace the ith row with, I just add, the ith basis vector plus a constant multiple of the other. So the column, right, goes to the column plus little constant times the second column. On the other hand, if I were going to do this on the target, so this is on the source, this is on the target, right? If I were going to change this one, Wi plus Cwj, what happens is that the jth row gets replaced by the jth row minus Cri. Okay, so yeah, so this is what you have to do. Okay, so now if we go back to our computation here, let's go back to our computation. Okay, so if we go back to our computation here, so what did we do? So if we start with, let's start with, we need a color. Okay, so we start with the domain here. So V1, or what did I call it? E1 prime. So we started with E1 prime, E2 prime on domain. Okay, and then on the codomain, we need to give that some letters. So we did that E1, E2. So E1, E2 on the codomain. Okay, so we did a row operation here. So the row operation here, let's see, this red row, so this, I don't know what color to use now. So this operation here, right? This is a change of basis. So this thing goes, this is a change of basis on the codomain. And it says R1, so it says that E1 tilde is equal to, so we had 3. So E1 tilde is equal to E1 plus 3E2. right? So I think that's correct. And then this one here. So let's check that this makes sense. Okay, so we're subtracting. So if we subtracted off R1 once, right? Then that would be adding E2 once. Okay, so to the first basis vector. So but we're adding E2 3 times, right? So that corresponds to this operation. Okay, so then this next operation here. Okay, so this is an operation on the domain, and so this says that E1 prime. So we have this thing is E1. Oh, sorry, C2. So we have this thing goes to E2 minus 2E1. Okay, so now this matrix, this thing here, 1, 0, 0 minus 2, is in the basis. Okay, so on the domain, we have is on the basis E1 tilde E2. Sorry, that's the codomain. I choose some nasty letters here. E1 prime, E2 prime tilde, and then this is the domain. And then we have on the codomain, we had E1 tilde, E2, E2, and this is on the codomain. Okay, so this is just E2. This thing was E2 minus 2E1. This thing, sorry, that's not the right way. This is E2 minus 2E1 prime. And then this is E1 prime. And then this thing was E1 tilde. So this is E1 plus 3E2. Okay.
I'm sorry, I've lost track of why exactly we're computing these.
Okay, so the reason I'm doing this is to show you how, if you wanted to show, okay, so I wanted to show you explicitly what the row operations we were doing was in terms of the linear transformation, right? So some problems may ask like, you know, what happens, so what basis do you use in order to put this into Smith normal form?
Okay.
Right? And so there's a certain change of basis that you'll use that gives the operation, you know, that puts the operation in the Smith normal form, and this is the basis that you do, right? So like, let's look at an example, right? So here, right? So our original matrix, what do we call it? A or something? I don't know what we called this matrix. We can call this matrix A, right? But if I do A of E1 prime, A of E1 prime, so this is, well, 1, 3, right? And this was, and then I used primes. Oh, sorry, E1. I used the terrible notation here. Well, E1 prime is E1 prime, I think. But A of E1 prime is this. This is, I forget what the notation is. This is 1, 3. Let's see what this is. Oh yeah, E1 prime is, so this is our basis here, right? And this is E1 tilde. So this thing is this thing. This is E1 plus 3E2. So this is this. Okay. And this is E1 tilde. Okay. So in the new basis, right, this thing just looks like it has a 1 there. You see? This is in the new basis. Okay, let's do A of, and now we have to do E2 prime minus 2E1. Right? If we did this, then this is just, well, this should be 2 E2. Okay, I claim that this is 2E2. So this should be 2, 0. Right? So that's what I'm doing, is I'm finding the explicit presentation, so that the explicit basis, so that it puts this linear operation into Smith normal form. All right.
Okay.
Okay. So like, where's an example of where you need this, right? So like, if like last semester when we were doing homology computations, right? This is the sort of thing that you'd need to figure out what homology groups are, right? So you can change what the basis on the source and the target, and so that you can compute what you know, what the homology is an example. And sometimes you want the explicit basis elements, because maybe it relates back to something you wanted in terms of your original basis, right? It's you know, I find in practice that you really, really want to keep track of your basis elements. All right. So, all right. All right. So one thing that I did want to say is, okay. So I want to state a theorem. I'm gonna state 2 theorems, okay, and then we'll talk about them next time. Okay, so this is about how rational canonical form and Smith normal form are related. So the relationship rational canonical form and Smith normal form. Okay, so let me state a theorem. Okay, so here's the theorem that I want to state. Okay, so let A and B be element of n these matrices over a field. Okay, so n by n matrices where F is a field. Okay, so the following are equivalent. Okay, 1, A and B are similar. Okay, 2, A and B have the same rational canonical form. Okay, so this means that they're similar. Remember, means that they're conjugate by an invertible matrix. And 3, that so Ti minus A and Ti minus B, and so now these are matrices with polynomial coefficients, right? Have the same Smith normal form. Okay, so these 2 things are the same. And so what's the thing that I really want to point out here, and I guess we'll talk about this more next time, is that the operations that the operations you're allowed to do on are completely different on these 2 things. So the operations for manipulations here. Are different. So here you need to conjugate by the same matrix, right? So in showing that two matrices are similar. In the bottom one, in 3, you can use any operations you want. You can use row operations and column operations and kind of like delete all the stuff. So you're So the bottom, the third thing about the Smith normal form is you're changing the two bases at the same time, right? The domain. I'm sorry, you're changing them independently, the domain and codomain. And then in the rational canonical form, you're to say that two matrices are similar. You're changing you're finding one basis for the range for the domain and codomain, and that changing one basis, since the domain and codomain are the same, you're kind of conjugating the two things. So this is about the presentation, right, of the polynomial matrix. So like the f of t module, and so this is about an f module thing, the top one. Okay. All right, so I'm a little bit over time, and I will stop and then let you guys ask questions